You know that feeling? You write code on your machine, everything works perfectly. You test it, debug it, polish it until it's flawless. Then you deploy it to the server, and nothing works. The code that ran flawlessly on your laptop crashes on production. Different Python versions, missing dependencies, conflicting libraries. This is environment drift, and it's the bane of every developer's existence. For decades, the solution was virtual machines. You'd install a hypervisor on your host machine, then spin up entire operating systems inside virtual boxes. Each VM gets its own kernel, its own memory allocation, its own everything. This works, but it's heavy. Each virtual machine needs gigabytes of RAM just to boot. You're essentially running multiple computers inside your computer. Want to run 3 different applications? That's 3 full operating systems, 3 kernels, 3 sets of system libraries. Your host machine starts groaning under the weight. Look at this. Each VM needs its own guest OS, its own kernel, its own system resources. They're completely isolated, which is great for security, but terrible for efficiency. And the boot times? Forget about it. Starting a VM can take minutes. Your CPU and RAM are maxed out, and you're still waiting for things to spin up. Then Docker came along and changed everything. Instead of virtualizing entire machines, Docker virtualizes at the application level. These red boxes you see collapsing? Those are the old virtual machines. And rising up? Those are Docker containers. Here's the key difference. Virtual machines each have their own kernel. But Docker containers? They share the host's kernel. Look at this, VM on the left, shared kernel in the center, Docker container on the right. The container is just your application and its dependencies, nothing more. Think of it like shipping containers. You can put anything inside a container: cars, electronics, food. The container itself is standardized. It doesn't matter what's inside, the ship can carry it anywhere in the world. Docker containers work the same way. Your application runs inside a standardized container, and Docker can run it anywhere: your laptop, a cloud server, a production cluster. Build once, run anywhere. That's Docker's promise. Write your code, package it in a container, and it will run identically on any machine that has Docker installed. No more "it works on my machine" problems. So how do you create a Docker container? You write a Dockerfile. Think of it as a recipe, a set of instructions that tells Docker exactly how to build your application's environment. You start with a base image using the from command. Maybe you need Node.js, so you use Node:20 Alpine. Alpine is a tiny Linux distribution, perfect for containers. Then you set your working directory with workdir. This is where your application code will live inside the container. Next, you copy your package files and install dependencies. This is smart. Docker caches each layer, so if your dependencies don't change, it doesn't reinstall them every time. Then you copy your application code. Notice how we copy dependencies first, then code? That's because code changes more frequently, so we want to maximize cache hits. Finally, you expose the port your app runs on, and define the command to start it. Expose tells Docker which port to listen on, and cmd defines what happens when the container starts. When you run Docker build, Docker reads this Dockerfile and creates an immutable image. Every layer is cached, every step is reproducible. This Dockerfile becomes your blueprint: build once, use forever. Let's clarify something important. A Docker image is not a container. An image is a read-only template, a snapshot of your application and its environment. A container is a running instance of an image. Think of it like this: an image is a class, a container is an object. You can have one image, but run multiple containers from it. See this? One image, 3 containers. Each container is isolated, has its own file system, its own network. But they all share the same base image, the same layers. Containers are ephemeral. You can start them, stop them, delete them. But the image? The image persists. Delete a container, the image is still there. Start a new container from the same image, and you're back where you started. And remember those layers we talked about? Images are built from layers. Each command in your Dockerfile creates a new layer. These layers are cached and shared between images, making everything more efficient. By default, Docker containers are isolated. They can't talk to each other, they can't access the outside world. They're like islands, completely separate. But Docker Engine creates a virtual network bridge. Containers can now communicate through this bridge, but they're still isolated from your host machine and the internet. Now your containers can talk. Your front-end container sends HTTP requests to your backend. Your backend queries the database. Data flows between containers through Docker's network bridge. But what if you want to access your container from outside? That's where port mapping comes in. Your container might be running on port 3000 internally, but you map it to port 80 on your host machine. Now users can access your application through the host's port 80, which Docker routes to the container's port 3000. Managing all these containers manually gets tedious. That's where Docker Compose comes in. You define your entire stack in one YAML file, your web server, your API, your database, all their configurations, all their networks. Then one command, Docker Compose up, spins up everything. One command, entire infrastructure. No more manual container management. Here's a problem. Containers are ephemeral. When you delete a container, everything inside it is gone. Your database container has 1.2 gigabytes of data. Delete the container, and that data disappears forever. That's where volumes come in. Volumes are persistent storage that exists outside your container. You attach a volume to your database container, and all your data gets stored there. Now watch this. We delete the container. The container is gone, but look, the volume persists. All your data is safe. You can start a new container, attach the same volume, and all your data is back. Volumes persist independently of containers. Behind all of this is the Docker daemon. It's the silent architect running in the background, managing containers, images, networks, volumes. You don't see it, but it's always there, orchestrating everything. The daemon handles all the low-level operations. When you run Docker commands, you're talking to the daemon. It creates containers, manages networks, handles storage. It's the ghost in the machine, making everything work seamlessly. This is where Docker really shines, in your CI/CD pipeline. A developer pushes code to GitHub. GitHub Actions triggers automatically. It builds a Docker image, pushes it to a registry, then deploys it to production. The old container shuts down gracefully, the new container spins up. Zero downtime deployments, every single time. And remember, build once, run anywhere. That same Docker image runs on your laptop during development, in your CI pipeline for testing, and in production. Laptop, cloud, edge devices, it doesn't matter. The container runs identically everywhere. Reliability, scalability, consistency, that's what Docker delivers. Docker, the ghost in the machine. Join us next time on the Binary Breakdown.